All right, so here we are for the first lecture for AP Biology at SFIHS. I will try my best to explain these things that you've been reading about and that you've been studying in a way that you can study on your own time. And if you have questions, you can email me or contact me through the website or text me or all of those things that we already talked about. So here goes. Let's talk about the chemistry of life, or as it's called in the textbook, the chemical context of life, which is just another way of saying it. You might come across it as biochemistry in some of the AP Bio books that I've given you. There's a lot of different words for it, but it's basically the same thing. But first let's talk biology, and then we'll talk about chemical biology. So when we talk about biology, what we're doing is we're talking about the study of life. The prefix bio comes from a word for life. So biology is the study of life and the study of living organisms. So that's not just humans, it's other animals, it's plants, it's fungi, it's bacteria, it's how they interact with one another, how they interact with their living environment. And so biology is basically answering a lot of questions about how living organisms live their lives. There are other areas of science. Biology is just one area of science, and if we are to divide science into three groups, maybe you're familiar with these subdivisions of chemistry, physics, and biology. What you'll find is, you can look at the world and you can understand it through the lens of biology, right? You can look at the world and understand it through life. But you can also look at it through chemistry, and you can look at how molecules and how chemicals interact with one another. You can also look at it through a physical lens, right? And so for our AP Bio class, we will focus primarily on biology. And within that biology, we'll look at a lot of areas. But right now, we're starting off in this section right here, in this chemical biology and this biochemistry, where we look at the chemicals that are involved in life, what chemicals are essential for life, and how they interact with one another to allow organisms to live, and what happens when they don't. So that's where we are, kind of. The other areas of science are very exciting, but that's not the scope of this course. So to start talking about chemistry and the biology where they meet, we gotta first make sure we got the language right. So there's a special kind of term that we like to use in chemistry, and you probably have already learned this already, or you've probably already learned this in your chemistry classes with Ms. Bueno. But in chemistry and in science in general, we like to talk about matter. And in reality, matter is just another word, fancy, special, whatever you want to call it, scientific. It's a word for stuff, right? So as biologists, you wouldn't necessarily refer to the stuff that you are studying. You would talk about the matter, right? So matter is our scientific word for stuff. And when we talk about matter, it's not just any stuff, right? There are certain qualities that stuff needs to have in order to be considered matter. And those two qualities are that it has volume and that it has mass. So if we're considering something, let's say we are considering this pen that I have right here, right? The question is it matter? Well, does it have volume? What does volume mean? We're not talking about sound. We're not talking about how loud your music is. We're talking about if something takes up space. So volume means to take up space. Wow, this handwriting. Okay, so how much space something takes up, right? So this pen that I have here, it has some volume, right? It takes up space. I can see it. I see that it has a certain size, right? So if something has a small volume, it is small. If something has a large volume, so let's say this cup that I have here, it has a larger volume than my pen. I don't know how well you can see this with the background, right? This cup is significantly bigger. It takes up more space than my pen here, and therefore my cup of tea has a larger volume, okay? And we can measure volume. And you can measure volume by calculating it, essentially, or you can measure it, well, one simple way to measure it is using water, if you have something that will sink. So here on our slide, I copy and pasted a picture. So this is a graduated cylinder, yeah. And it has, 200 milliliters of water in it, right? And if we put I think that's a rock, I don't know, something in it that sunk, our water rose up to 300 milliliters, right? So the water level went up because of this thing that we put inside of it. We did not add more water, we just added that rock. And so that means that our rock has, if we do our 200 milliliters subtracted from that, our rock has a volume of about 100 milliliters. That is its volume. That is how much space it takes up, right? That is a simple way to measure volume, but it's one way to kind of think about it. How much space something takes up. Matter must have volume. Great. The other one that matter must have is mass, right? It must weigh something. So if we put something on a metric scale, let's say we take this rock and we put it right here on our little scale, right? This should measure that it has some kind of a mass, if it's not broken, that is. So let's say it has 10 grams, right? Volume, mass is measured in grams or kilograms or milligrams. I'm sure you've come across a lot of those in your home countries. They are not used in the United States as much as they should be. For some reason, we use pounds. In any case, matter has to have both of those things, right? If it has only one or the other, which doesn't really happen, but theoretically, it's not matter. So one way that I like to think about matter to help kind of decide if something is matter or not is that I imagine a jar, and I imagine if I can put whatever at hand in jar. So for example, here we have my picture of a jar, and so water, right? Is it matter? Is it not matter? Well, if you could take water and you can pour it into the jar and fill that jar up with it and hold it in there, it's matter, right? And we know water is matter. That makes sense. It has volume, it has mass, easy, right? What about air, right? Can we put air inside of a jar? In fact, sometimes people get confused by this, but the reality is that we can. Air definitely has a volume. It takes up some space. It fills up the spaces that we're in. This room that I'm in is filled with air. And if you measured its mass, it wouldn't have a big mass, but it would have a mass nonetheless. So in fact, water and air are both examples of matter. However, if we take our jar and if we put, could we put emotions into it? Like if I was angry, could I fill up a jar with anger? And although maybe we say that as an example of some kind of figure of speech, right? Like I've been drinking a cup of anger. I don't know if that's actually a figure of speech, but it could be. Anger, in fact, you could not put into a jar. It is an emotion. It does not have a mass. It does not have a particular volume. It is important. It does matter to us, but it is a non-example of matter. Okay? And so that's all great, pretty straightforward, matter. But when we talk about matter, it turns out that matter is actually made up of stuff. It's not all the same. It's not all made out of the same type of material. Matter, in fact, is made up of the elements. So we can look at the elements in our fancy periodic table that I got from P-Table. I don't take credit for having this. This was copy and pasted. So matter is made out of the elements, okay? And we can organize those elements into our fancy periodic table of elements, and it has all kinds of patterns that we can learn to read, and it's really exciting. And we're not going to really do that much in this class, but we need to, be relatively familiar with the idea of elements. So there are about 116, I'm not sure now, some 100-something number of elements that we know about. Most of those elements are natural, Let's go pen. Naturally occurring. There are 92 of those, right? The other, however many are left over, 20 something or other, are synthetic. So those are made by humans, and we're not really going to talk about them in this class. In fact, we're actually not going to talk about most of the elements in this class. There are only about 25 of the elements that are absolutely essential for life, which means without them, organisms wouldn't be able to live. Not every single organism needs every single one of them, but of the 100-odd elements, 25 of them are really important for life and for the study of biology. And we're going to talk more about what kinds there are, but first I want to talk about what happens when elements come together, right? Because these elements can live, or live maybe is the wrong word, exist individually, just, as an element by itself, as a pure substance. But the reality is that they actually spend a lot of time interacting with one another. And when they interact with one another, they sometimes form compounds. And that's really important to understand. And again, a lot of this stuff should be review from your chemistry class, but it's always good to review it. So let's see, what color do I want? So red. No, actually, not that one. Blue. Okay. So when we see elements coming together and they bond, so they make connections in specific ways, we can call those compounds, right? They are compounded elements. They have come together to form one entity from multiple things, right? And a classic example that they always talk about in chemistry class, and I guess in biology class now, is sodium and chloride coming together to make sodium chloride. So sodium, symbol is Na. If we go back to the periodic table, I can point it out for you guys. You should remember, though, that it's in group 1 right here, sodium. And it is a metal, specifically an alkali metal. And if you've ever seen it, maybe in a video, maybe in real life, you would know that sodium is a soft metal. It can actually, you can take a knife or like a butter knife and you can slice it and it reacts really intensely with water, which is great. So we have our sodium here. And then we have another element, chlorine. And again, I can point that out to on the table, but you should remember that that's in group 7. And sometimes we call group 7 the halogens. And so we have chlorine. Ooh, I did not want to do that. We have chlorine right here, right? So we have chlorine and we have sodium. So chlorine at room temperature is a gas. Gas at RT means room temperature, which means a temperature that rooms often are in, a temperature that rooms often have, which is usually 25 degrees Celsius. So it's a gas, and it's actually a pretty disgusting gas that you wouldn't want to spend much time or any time at all breathing. And it is a nonmetal, which you probably should remember, given that it's in group 7. And so individually, these two different elements have very different characteristics. They have very different properties, right? Metal, non-metal, gas at room temperature, solid at room temperature, reacts with water, does terrible things to your body, so they have different properties, right? But they can come together in a chemical reaction, right? And they can form a compound. And in that compound, we can take a sodium and it can bond with a chlorine, right? They're not just hanging out together, they have a bond between them. And that makes a compound that we call sodium chloride, which is in fact table salt. Yay. Which, I mean, you shouldn't eat tons of it, but overall it's not a dangerous substance. Well, I mean, if you ate like a lot of it, then it would be dangerous, but we know what we're talking about here, right? It's you can eat it. And we write the chemical formula for that as NaCl, right? Same thing right here, and we call it sodium chloride. And the point of what I'm trying to say here is that elements come together and they form compounds that can be very, very different in terms of their properties from the elements that they came from. And that all depends on what ratio what elements and what ratio they are connected in, right? So when you have one sodium and you have one chlorine coming together to make one compound, that is sodium chloride, right? If you had chlorine coming together with a different metal, it would form a different kind of compound and it would have different properties. And it turns out that you don't always have just two things coming together, right? Our compound is made out of two or more elements together, right? Connected with bonds. So you might remember a compound from your biology classes before, C6H12O6, which is glucose. Sometimes we just call it sugar, but you'll learn much, much more about glucose. And glucose is a really, really important compound of carbon, hydrogen, and oxygen. But it's not just carbon, hydrogen, and oxygen connected to each other just randomly. There are 6 carbons, there are 12 hydrogens, and there are 6 oxygens. And you'll learn later on that those 6, 12, and 6 elements are connected in very specific ways, and depending on how they are connected, they do different things, right? So compounds form between elements, and they are connected in specific ratios, right? So it's not a random number of carbons, it's not a random number of oxygens, they are very specific ratios. Our sodium chloride is in a ratio of 1 to 1. 1 sodium for every 1 chlorine. In our glucose, it's in a ratio of 6 carbons to 12 hydrogens to 6 oxygens. And we need that ratio to make glucose. If we wanted to make something different, it would be a different ratio, right? So that's all about compounds. But now let's talk about biology. Let's focus in on biology and the elements that are involved in biology. So you're like, all right, miss, got it. Ratios, compounds, elements. 25 of those elements are essential for life. Whoop-de-doo, right? But let's take a look at a example. So, for example, let's look at a table, a wooden table. And this wooden table is made out of a tree, right? Or was a tree, I guess. It's a real wooden table, let's say. And you might be thinking, okay, great, tree, living organism. So what elements is it made out of? It's one of those 25 elements that we had, right? But it turns out that this table is made almost entirely out of 4 elements. And those 4 elements are carbon, hydrogen, oxygen, and nitrogen. CHON, as I like to remember them. And it's not a word, as far as I know, maybe in another language, but I just remember the word CHON, and it helps me remember that it's carbon, hydrogen, oxygen, and nitrogen. I hope you can read my handwriting. If you can't, then use your periodic table, right? And so what we find is that 96% of life or living organisms is made out of CHON, right? So this table is made out of cellulose, and cellulose is a carbohydrate that's made out of glucose. And glucose, as we know from the previous slide, is C6H12 and O6. Yay. I'm glad that you remembered. Right? So it's C carbon, hydrogen, and oxygen, right? And there's also some nitrogen in there, but it's mostly carbon, hydrogen, oxygen, right? You also are made mostly out of carbon, hydrogen, oxygen, and nitrogen. If I could measure what elements you're made out of, it would, I can't do that actually without you not living. But if I could, then I would see, let me draw a person because this is nobody specific, it's just a person in general. It's kind of hard to draw on a computer. All right, I'm going to label that so you know what this is. It is a human, right? So of this human, let's say the vast majority of it, 96% of this human, is made out of carbon, hydrogen, oxygen, and nitrogen. Okay, this is hard. Okay, right. And that's remarkable. And remember that we're talking about 4 elements, but they are connected in different ways, right? They are different compounds. And there are, I don't know, thousands, millions of different compounds that you have in your body. And even though they're made out of mostly these elements, they're connected in different ways and they can do different things. And so you might be saying, okay, well, that's great, miss, but what about like the other 4%? And it turns out that the other 4% is made up of actually, this is the 4% that I'm talking about, 4%, is made out of another 7 elements, right? So it's not a huge number of elements. Those elements are calcium, they are phosphorus. Let's see if I can remember them all. We have potassium, sulfur, sodium, and chlorine, and magnesium, right? So these other elements are also really important for life, and they make up, some percentage of who you are and what, other organisms are. But again, the majority, most of the elements that you are made out of are carbon, hydrogen, oxygen, nitrogen. And you might be saying, well, that's kind of cool, but like, where do I get that anyways? Well, if you think about food, like, let's say you eat a piece of bread, bread is made up of mostly, there's a lot of cellulose in it, there's glucose in it, right? And that's mostly carbon, hydrogen, and oxygen. Nitrogen is also found in food, and especially it's found in protein, and we'll learn more about that. So the food that you eat is mostly made out of these elements as well. And then think milk has calcium in it. That's good. Bananas, they have a lot of potassium in them, right? Sodium, salt, sodium chloride, right? Sodium and chloride, actually. So all of these elements come in through the food that you eat. And it makes sense that you would get that from your diet. Let's see, lost my train of thought because I got an email. Doop-de-doo. Okay. So we talked about the essential elements for life. We said that they're mostly made out of, our life is mostly made out of carbon, hydrogen, oxygen, and nitrogen. Then we talked about the other important elements. And now we're gonna talk about something called the trace elements, right? So let me just write this here for us. So we have actually I should use the same colors that I did before. So we said, what is it, blue? So we had the 96%, wait, why are you so, I don't want that, I want you to, 96% are the Chan. And then we had our 4%, which was the other 7. I did the wrong color again. Okay, I'm going to try this one more time from the very beginning. Okay, so we have our 96% Chan. And now I used red, I think, for the other one, right? Then we had our 4% for the other 7 ones, right? And I could circle those for you, right? So we have sodium here, we have magnesium here, we have calcium, we have potassium, we have chlorine, we have sulfur, and where is the last one? Doop, 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 doop. I'm totally spacing out on which one it is. Oh, here, phosphorus. Dink. And I'm going to circle our Chon. Oh, hey, look, they're like really close to each other. Anyways, so we have those. And then we have something that we call trace elements. I'm going to use green for that one. I hope you can read that. Trace elements. And when I say trace, I'm not saying like, you know, like outlining the borders of something. Trace, I mean as in tiny, tiny amounts, right? It's a word that we use to say very small amounts of something. And there are certain elements that you need small amounts of, but you really need those small amounts, right? Like it's not like you can go without those small amounts. It's like an optional thing. No, it's like if you don't have those small amounts, your life, well, you might die, or you would be very sick. So you had a table in your reading that listed off all of these. All of these trace elements. So if you flipped into the textbook, it is on page 32. You have a table that shows these trace, well, it shows all of these. So less than 0.01% of a human body, and it's similar in other organisms, is made out of these elements. So we have boron, we have chromium, we have cobalt, copper, fluorine, iodine, iron, manganese, molybdenum, selenium, silicon, tin, vanadium, and zinc, right? So these are all elements that you need, but you don't need a lot of them. You just need a teeny little bit. So you might be asking, well, that's interesting, but like what happens if you don't get enough? Like what kinds of things happen, right? And so in the textbook, it talks about what happens if you have an iron deficiency, it talks about iodine deficiency. And so one of the possible things that can happen if someone has a deficiency in iron, meaning that they don't have enough iron. Let me move this so it's like not in the way. There we go. So if they have a deficiency, that means that they don't have enough. They lack. So it's like not enough iodine in their diet. Then it affects an organ that is called your thyroid gland. And I don't know if you can read that, but let me write it out here so you can read it. Thyroid gland. And we'll learn more about this later. The thyroid gland is a really important gland. It regulates your metabolism, so that has to do with like how much you digest. It has to do with your heart rate, your body temperature. All kinds of very important processes are controlled by the chemicals that this gland makes, and it needs iodine. In order to do that, it needs to have iodine, and it doesn't need a lot of it, but it needs some. And iodine, turns out, you can get quite a bit of it in seafood, and other products as well, but seafood is like a big one. And so in areas that are landlocked and they don't have as much access to seafood, sometimes there have been, especially in the past or in other countries, not so much in the US anymore, which I will explain why, you have seen that people did not get enough iodine and they developed something that's called a goiter, which is this kind of like enlarged area on their neck. And the reason why it's enlarged is because their thyroid gland gets bigger, and it's like a swollen thyroid gland. And it's a pretty serious condition, and that comes about when people don't have enough iodine. And so this happened in the United States, like in the early 1900s. And then a doctor came along and decided to try adding iodine to salt. And we don't need to really get into how they added the salt per se, but maybe you're thinking about halogens and alkali metals making salts. But the bottom line is that you can add iodine to salt, and it doesn't change the way that the salt tastes. And so this started a new kind of way of producing salt in the US and in other countries as well. And so now they sell iodized salt, which means that it's sea salt, or any salt really, that has iodine added to it to help people avoid having this lack of iodine in their diet. And so that kind of solved the problem in the US, and in countries where they sell iodized salt, they see a lot less of this type of condition. So that is an example of what happens when you don't get enough of a trace element. Again, you don't need a lot of it, you just need a little. Another example that we don't really need to go into too much depth, but maybe you've heard of, is if a person does not get enough iron, right? So again, we can remember that iron was one of our trace elements. You need it especially in your blood, because iron is the element that allows your blood to carry oxygen around your body. And if you don't have enough iron, one of the things that happens to people is that they become anemic, right? They develop anemia, which means that they don't have enough red blood cells. And that can cause a range of problems, right? The thing that people usually notice first, when it's not too severe, is fatigue, right? They feel like they are tired all the time. And you can imagine why. If you're not getting enough oxygen to all the muscles that need to get that oxygen, you're going to feel tired, right? Another symptom, or another thing that people often have, is that you might notice that they're kind of like pale and that they are cold, right? So I've been anemic in the past, only mildly anemic, but you're tired, you're cold, you're kind of pale all the time. And then if you change your diet, if you are more careful about your diet and you make sure to eat foods that are high in iron, which might be various vegetables like broccoli and spinach, or if you eat meats, then it could be beef, pork, chicken, eggs, if you're into liver, that too, right? So by changing your diet, you can decrease the problem, right? And now it's not really a problem in my life. So the point is that you get these elements from your diet, from what you eat. That is how these elements get into our body, and that's how we are able to use them. So by eating and by drinking, we are getting all of the elements that we need, and so organisms need to be careful that they are getting all of the elements that they need in their diet. And I think that's all I want to talk about with you. So we talked about the essential elements. So let's do a little bit of practice. I would recommend pausing the video to answer the questions before I give you the answers. So the first question is, what does the word trace mean? Is it A, an element that is needed in tiny amounts? Is it B, an element that can be used to follow the path of an atom through an organism's body? There should be a apostrophe here. Or is it an element that is healthy but not essential for an organism to survive? Or is it an element that just passes through your body really quickly and isn't absorbed? So the word trace, what does it mean for an element to be a trace element? Now that you've thought about it and you've answered after pausing the video, you will know the answer is a trace element is an element that you only need in tiny amounts, right? Very important, it's essential, but you only need tiny amounts of it. So we have another question. And this is not a multiple choice question because you got to practice those too. I'm going to use a different color because green is not good. So we talked about how there are 25 elements that are needed for life. And my question for you is, what are the 4 elements that make up 96% of living organisms? So what are the 4 elements that are most common among organisms? Now you're going to pause the video, right? Now that you've stopped pausing the video and you've written down a thorough answer, you can compare yours with mine. So you'll remember CHON, which stands for carbon, hydrogen, oxygen, and nitrogen, right? So these are the 4 elements that are absolutely essential for life, that make up most of you, me, the animals around you, the trees, the other plants, the bacteria, the fungi, and any other organism that I'm forgetting. Okay, so CHON, don't forget it. Now you have a tricky question, and don't let them trick you because it sounds like it's tricky. So, here's a question that's asking you, which of the following elements is needed in trace amounts by animals and vertebrates? Is it A, nitrogen, B, calcium, C, iodine, D, sodium, or E, phosphorus? So take a moment, pause the video, think about your answer. Feel free to write on here. Process of elimination is always a good strategy. And now that you've paused the video and written an answer, here is the answer. So first of all, this is the type of question that you might see on the test. It's trying to trick you into thinking that they are looking for a different answer than the one that you know is right by saying animals and vertebrates, right? They're not saying all living organisms. They're saying specifically animals and vertebrates. And vertebrates are just organisms that have a spinal cord. And so you might be thinking, oh yeah, but what about like the jellyfish? Wait, actually no, that would still count as an animal. Damn. What about the bacteria? But ignore that part because they're trying to trick you there. And instead focus on the fact that they're asking about a trace element, right? So you're looking for a trace element. So you know it's not nitrogen, you know it's not phosphorus, you know it's not calcium, you know it's not sodium, because those are not trace elements. Nitrogen is one of the CHON, and then calcium, sodium, and phosphorus, you'll remember from the list of the elements that make up the other 4%. And so you know the answer is iodine because iodine is a trace element. So hopefully that made this clearer and not more confusing. And that's all that I have for you so far. I'm going to go work on the next video now, so I hope that you enjoy this one, and good luck studying.